So let's start with our next session, which is on the energy and environment related to SDG goal number 7 and 13. The next speaker is Professor Anita Ho-Baillie. She is the Professor John Hook Chair of Nanoscience at the University of Sydney, Sydney Nano member as well, will give a talk on perovskite solar cells. Anita, please.
Thanks, Santa. Good afternoon and good morning and good evening to people who are attending my talk. Thanks for coming. So I'm going to talk about briefly an introduction of perovskite and perovskite cells, and then touch on a little bit of what we do in our lab. So metal halide perovskites have been discovered 100 years ago, and it was discovered to take the form of this crystal structure shown on the right-hand side. So, but it's only until recently, about 10 years ago, that people found that it can be used for photovoltaics and solar cells, and that's because it's got a very good optical absorption. What this means is it can be made into very thin films. So compared to the conventional silicon solar cells is around 200 to 500 times thinner. And what makes it so good is also we can tune the composition to tune the optical properties. So the blue circle here is the cation, so it could be in the form of cesium or methyl ammonium or from a vanadium. So it could be an inorganic perovskites or an organic inorganic hybrid surrounded by these lead halide cages. So if we're able to tune the composition, to tune the band gap, what it means is we can absorb different parts of the solar spectrum. So it means that we can stack different types of perovskite on top of each other to form a tandem. And by doing so, the high band gap cells will be able to absorb the, for example, the blue part of the spectrum better, and then the low band gap perovskite will be able to absorb the long wavelength better. So on the right hand side, you can see that if you have just a material of one type, what we call the single junction solar cell, the maximum efficiency is around 33%. But if you stack two materials on top, together, then if you have a band gap, ideal band gap of around 1 eV and 1.7 eV, you can have an efficiency as high as 45%. And if you have three stack tandem, the efficiency can be 51%. So the band gap will be around 1 EV, 1.5 EV, and around 2 EV, and so on. So you can see the efficiency keeps improving by around 10% until around 4 junction tandems. Then the increase will be marginal. So what also makes this material so interesting and exciting is it's very easy to make. So here you can see one of my students trying to make the material. So what you do is you mix the organic precursor with the inorganic precursor, so in the form of salt. You dissolve them, mix them together, and you just deposit it onto a substrate. And you can see the film turns from clear to black, almost black. It means that it has turned into a photo-absorbing material and it's photoactive. So you can see that it's a black film, and then this one, you can see the student is spraying instead of dropping it onto substrate, spin coating it. You can see it turns orange. So this material's got a higher band gap around 2 eV, so it absorbs the orange part of the spectrum. And then the top film's got a lower band gap, so it absorbs most of the visible light. So the bottom is a cesium lead aldehyde bromide 2, and then the top was a methyl ammonium lead aldehyde 3. So I'll move on. So it's the deposition method used can be also very versatile. So we just about try every method that we can put our hands on. So we've done dropping, spin coating, and then spraying. We've done thermal evaporation in vacuum, of vaporization in ambient. We've also done blow drying, so this is air, and we also have a blade coater as well. Another thing is also very versatile in terms of the cell structure. So the substrate, or what we call the superstrate, because the lights go through the substrate, can be rigid or flexible, can be glass or can be plastic. And you just need to sandwich the perovskite with an electron transport layer and hole transport layer with electrodes as well to conduct the electricity. So you can see it opens up imaginations. People can be very creative in the way they use perovskites for building integrated photovoltaics or vehicle integrators, or even in space because of the lightweightness and also the flexibility. So another thing that attracts people to conduct research in this area is it only took 10 years for the perovskite cell efficiency to double, whereas for the incumbent silicon, it took 40 years. So you can see that, so people get very excited. My students can make cells in the lab, and it doesn't take them long to make a 20% cell. So we've got recently been awarded 2 projects funded by the Australian Renewable Energy Agency. So we have experience of fabricating perovskite and silicon tandem. So you can see the publications there. And we've recently won a project to look at perovskite silicon tandem. So you can see 3-junction here with the aim of boosting the efficiency further. So you can see that there are a lot more layers, there are a lot more interlayers, and therefore it's a lot more fiddly to integrate all those cells together. So it's easy to draw it on a cartoon, but actually making the cell and in the process of not damaging the cells and also having efficient transport between the layers is quite tricky. Also, optically, we have to optimize the layers because they all have different optical constants, and also electrically as well. And as we move on to larger areas, we've got to think about metal grid designs and optical losses and shading losses, etc. We're also awarded another project of looking at stabilizing perovskite cells and perovskite tandem in this case. Because perovskite is easy to make, it can degrade easily if we're not careful. So I will talk about the polymer glass encapsulation that we have developed, managed to stabilize the cells. But in this project, we're looking at the polymer-free glass encapsulation by bonding 2 pieces of glass together at low temperature, because perovskite doesn't like very high temperature. So that's one challenge. So there's new glass technology and also new knowledge about how to stabilize cells. The photo shows a perovskite silicon tandem cell that is in the CSIRO site in Newcastle, sitting outdoor, being tested for its durability against the harsh environment of rain and sun and heat and cold. So I'll talk about one of the recent work that we published about durable perovskite cells. So looking at the Incumbent technology silicon solar module that you buy off the shelf, they give you 12 to 15 years of product warranty and 25 to 30 years of performance warranty. So it doesn't mean they don't degrade, but it's just a set amount of value that the performance will drop over time. So with perovskites, they can be quite sensitive to moisture, and they can be thermally unstable. So what we did is we try to understand what happens when they are being stressed thermally, what are the pathways to decomposition. And if we understand how they decompose and what can stop them from decomposing, we can develop destabilizing strategies, and in this case, encapsulation. And I will explain why encapsulation actually helps the thermal stability. So first of all, we used this technique called gas chromatography mass spectrometry to look at the decomposition products. So it's not a new technique. It's been used for developing new drugs or testing drug cheats or detecting explosives, or even analyzing soil samples en masse. So GC is used to separate a chemical mixture, a mixture of gas, and the MS is to identify the components. So here, if you remember that to make a perovskite cell, you need the precursor. So you need the organic halide, salt, and then the inorganic lead iodide salt. But in this case, we don't need to analyze the lead halide salt because they won't give out any volatile products. So we analyze the 4 precursors. So the methylammonium iodide, the formamidinium iodide, and the methylammonium bromide, and then the mix. So the mixed cation, the mixed organic cation, and the mixed halide, they are the sort of state-of-the-art perovskite materials for the high-performance cells. So we heat those precursors in a bottle and at different temperatures and look at what happens. So look at what comes out. So we can see that there are 4 main signature products that come out. So the CH3I is mainly from the MAI, the HCM from the FAI, CH3 from the MABR, and ammonia comes out of every single precursor. And then we can, from the signature products, we can look at the composition pathways. So some of the things that we can sort of, go into the detail, but I'll just talk about the really 2 key main findings. So you can see that the ammonia is lowest for MABR. And what it says is MABR is more stable, and we do find that. So if we mix MAI with MABR in very early research, maybe 7 years ago, people found that it stabilized the perovskite cells. And also these methylamine also comes out as an intermediate product. So as a very small amount, it can't be detected. But what is important is it comes out of the MAI, and having that actually will react with the product of the FAI and then drives the decomposition reaction here at 5. So if you don't have MA, the FA type perovskite is quite stable. But as soon as you mix MA and FA and you have this intermediate product, it will drive the decomposition of FA, making it irreversible. So that's the case too, as a lot of research have found that FA is less stable compared to FA, and if you put MA with FA, it makes it less thermally stable. And in this work, we're able to find out why. So the mechanism behind it. Also, cesium doesn't outgas. So what it means is if you have cells that's got cesium, FA, without the MA, these cells will be more thermally stable. And we're able to sort of quantifying it, show it, rather than just by intuition. So what happens next? So now we know how they decompose. We are looking at 2 kinds of different encapsulation schemes. So both of them use a polymer-based materials. It's either polyisobutylene or polyolefin. They're commonly used for like double glazed window as an etch seal. So we use it as an etch seal, or we use it as a blanket, so cover the entire back of the cell. And look at the difference. So here we use the FTO as the feed through. So the electrons and the current and the photons have to come out, and we rely on the FTO to conduct the current. So you can see that on the right hand side, you can see a void in there. So what happens? So then we look at the test cells that are control cells that don't have encapsulation, and we'll also look at the cells with encapsulant only, and then an encapsulant with glass. So typically you'll want a module to have glass on both sides for rigidity, if used for example, solar farms or even solar window. So this time we look at the cesium FAMA, and as expected, they outgas 5 times less. We also look at this whole transport layer PTAA. So PDA is slightly more expensive and a less commonly used whole transport layer. But encouragingly, we found that PTAA doesn't outgas. So at least at 85 degrees, which is the typical operating temperature of solar cells. And we also found that if you have just the encapsulant without the glass, you will see outgassing. So these second and the third sort of histograms, you can see the outgassing of the signature products. And if you have glass, there's hardly any outgassing. And if you use the polymer as an etch seal, you will get a void there. And by sort of probing into the void and sampling the gas there, we found there are signature products. So what we found is, one more thing is PO is more effective than PIB in terms of suppressing the MA-related products, but PO is more permeable to a commonly found signature products NH3. So it could be there's various ways of explaining it. Could it be that PO just absorbs ammonia better, and we need to find out more. So what we found is the blanket encapsulation is much better than the etch seal. So what it does is it creates a pressure-tight environment, so to stop the perovskite from outgassing. So why is it important? It's actually the outgassing that drives the decomposition. So if we can stop the outgassing on this track, we can actually stop the decomposition. This is something that we suspect a few years ago because this is an encapsulating scheme that we've used. We managed to get the cells to pass the thermal cycling test required by the standards, but we didn't quite understand why the blanket scheme is better than the void scheme. So we suspect that there's outgassing happening, but this time we're really able to confirm it. So it does two things. The blanket encapsulation stops the thermal outgassing, but it also improves the moisture resistance by stopping moisture ingress. So using this scheme, we torture the cells again according to the IEC standard. So last time we managed to pass the thermal cycling. This time we subject them to dam heat and humidity freeze. So dam heat involves 85 degrees at 85 relative humidity for 1,000 hours. So if you see only 5% drop in efficiency, then you pass the test. But we managed to exceed the requirements by 700 hours. With the humidity freeze test, what we do is there's a prerequisite thermal cycling where you've got to thermal cycle the cells between -40 to 85, 10 times. And then you freeze the cells very quickly to -40 and in humid conditions. So basically you deliberately have condensation. So if there's any water crystals within the cell or within the encapsulating material, will form crystals and sort of wreck the encapsulation. So the requirements is 30 humidity freeze cycles, and we managed to exceed that by almost 3 times. So that was quite a breakthrough for the field, and we were able to publish the work in Science. So that's it for my talk for today, and I'd like to thank you all for paying attention. Thank you.